Intergalactic space is the enormous expanse that exists between galaxies. Unlike the crowded and energetic environments inside galaxies, intergalactic space is mostly empty. It is a place where stars, gas, and dust are spread far apart. While galaxies are packed with stars, planets, and other matter, intergalactic space has very little of that. It's essentially the void that separates one galaxy from another. Imagine standing in a vast field. Around you, there are trees, flowers, and animals. This is like a galaxy. Now, step outside that field into an area with hardly anything around. It's quiet, empty, and devoid of life. This is more like intergalactic space. In this space, there are very few particles, and most of it is completely devoid of any significant matter. The space between galaxies is so vast that the nearest galaxy to our own, the Andromeda Galaxy, is still about 2.5 million light years away. Despite how empty intergalactic space may seem, it's not entirely void of matter. Even in these large stretches of emptiness, there are trace amounts of hydrogen gas, magnetic fields, and cosmic rays. These components make up what scientists call the intergalactic medium. It is a thin, sparse web of particles scattered across the space between galaxies. But even though this matter exists, it is spread out so thinly that it's almost invisible to the naked eye. The vastness of intergalactic space is almost impossible to comprehend. The distance between galaxies can be millions or even billions of light years. A light year is the distance that light travels in 1 year, about 5.88 trillion miles. So when you think about the distances between galaxies, it becomes clear that the space between them is immense. This emptiness is what makes intergalactic space such a mystery for scientists and astronomers. Within galaxies, stars and planets orbit around a center of mass, and gravity holds everything together. In intergalactic space, however, gravity is much weaker because there is far less matter to exert gravitational pull. This means that objects in intergalactic space, like individual stars or even small groups of stars, don't have the same kind of attraction or motion as objects within galaxies. These stars are often isolated, moving alone through the vastness of space. While intergalactic space may seem lonely, it's not without activity. In fact, one of the most powerful events in the universe can take place in this empty space. When galaxies collide, they send shockwaves through the surrounding intergalactic medium. These collisions are incredibly energetic and can create massive bursts of light and radiation. Even though the space between galaxies is largely empty, it can still be affected by the movement and interaction of galaxies. For example, when two galaxies collide, the gas within them can compress, heat up, and produce new stars. This process can trigger a burst of star formation, even in the midst of intergalactic space. Another thing that happens in intergalactic space is the movement of dark matter. Dark matter is a mysterious substance that makes up a large portion of the universe's mass. It doesn't interact with light, making it invisible to us. Scientists know it exists because of the gravitational effect it has on galaxies and clusters of galaxies. Dark matter moves through intergalactic space, pulling galaxies toward one another, helping to shape the overall structure of the universe. While we often think of space as being completely empty, the reality is more complex. Even in the emptiest regions of space, there are still forces at play. These forces, like gravity and dark matter, help shape the universe in subtle ways. Galaxies that seem isolated in intergalactic space are actually part of a much larger structure. These galaxies are linked by invisible forces that bind them together into cosmic webs. The galaxies may appear to be scattered, but in reality, they are all connected by these unseen threads. Intergalactic space is also a place of quiet cosmic evolution. In the voids between galaxies, there's little to stop the movement of galaxies themselves. they drift through the vast emptiness, sometimes forming clusters of galaxies that are bound together by gravity. These clusters are some of the largest structures in the universe. They can contain thousands of galaxies, all held together by the weak but steady pull of gravity. As galaxies move through intergalactic space, they sometimes interact with each other, merging or exchanging stars and gas. These interactions can lead to the formation of new structures and even new galaxies. The study of intergalactic space is also important for understanding the broader cosmos. The voids between galaxies give scientists a unique opportunity to study the universe's largest scale structures. Because there is so little matter in these regions, scientists can study the effects of cosmic forces without the interference of stars and other objects. By examining the way galaxies move through these voids, scientists can learn more about the behavior of gravity and dark matter, two of the universe's most elusive forces. In essence, intergalactic space is a crucial part of the universe's structure, even if it seems empty and silent. It's where galaxies are born, collide, and evolve over time. The vast stretches of nothingness that we often think of when imagining intergalactic space are far from barren. They are the stage for some of the most dramatic and far-reaching events in the universe. The emptiness we see is just one aspect of a much more dynamic and interconnected cosmos. Though intergalactic space is not as flashy or visible as the inside of a galaxy, it plays an essential role in the overall story of the universe. The emptiness of space is full of invisible forces, subtle motions, and unseen connections. As scientists continue to study this vast, uncharted expanse, they will uncover even more mysteries hidden in the void. Understanding intergalactic space gives us a glimpse into the quiet yet powerful forces that shape the universe around us. Cosmic voids are vast, empty spaces scattered across the universe, usually found at the edges of galaxies and large-scale cosmic structures. These voids are often described as underdense regions because they contain far fewer galaxies and stars than other parts of space. They can be huge, stretching across hundreds of millions of light years. Despite their emptiness, cosmic voids play an important role in shaping the universe as we know it. Imagine you are looking at a map of the universe. A map filled with clusters of galaxies connected by large threads of matter. In between these clusters, you would notice large, almost blank areas. These blank spots are the voids. They are the spaces between the cosmic filaments, which are made up of galaxies and gas. It's almost like a network of interconnected webbing, and the voids are the open spaces in between. While galaxies and stars fill most of the universe, these voids are noticeable by their lack of visible matter. A cosmic void can be thought of like a desert in the universe, where very few galaxies roam. The emptiness is so extreme that in some voids there may be as little as one galaxy for every 100 million light-years. To put this in perspective, our Milky Way galaxy, which is filled with billions of stars, would be just one speck of light in such a vast region. What's even more interesting is that these voids don't just contain fewer galaxies, they are also larger and more expansive than most people imagine. Some of them can stretch for hundreds of millions of light years across. To give an example, the Bo-Phi-Tes void, one of the most famous cosmic voids, is about 330 million light years in diameter. To put that into perspective, if you could travel at the speed of light, it would still take you 330 million years to cross it. This makes cosmic voids some of the largest known structures in the universe. Despite their size, cosmic voids don't appear as empty as they might sound. They still contain some matter, but it's so spread out that it is almost impossible to see. Most of the matter that fills these voids is in the form of dark matter and diffuse gas. These elements don't emit light the way stars do, which is why we can't see them directly. The matter in cosmic voids is so thin that it can barely be detected. The lack of visible stars and galaxies combined with this sparse distribution of matter, gives voids their characteristic emptiness. One of the key features of cosmic voids is their ability to influence the movement of galaxies. Although they appear to be empty, they still exert some gravitational pull. This pull is not strong enough to cause any noticeable effect within the void itself, but it does affect the galaxies around the void. In fact, galaxies that lie on the edges of a cosmic void tend to move away from it. This is part of the larger scale structure of the universe, where galaxies are slowly being pulled toward denser areas, like clusters, and away from the voids. This movement also explains why voids are not completely devoid of matter. The gravitational pull from nearby regions can cause galaxies and other cosmic structures to move towards the denser parts of the universe, leaving the voids even emptier. But galaxies inside or near the voids can also be affected by these movements, as they are drawn toward the cosmic filaments that surround the voids. This creates a push and pull dynamic that shapes the overall structure of the universe. In a sense, cosmic voids help define the shape and layout of the universe. They are the spaces between the clusters of galaxies, making the universe look like a vast interconnected web. The filaments of galaxies are spread out across the universe, and the voids are the open spaces in between them. Without these voids, the universe wouldn't have the same large-scale structure. The voids give the universe a kind of cosmic balance, with dense clusters of galaxies existing alongside vast, empty regions. Another interesting aspect of cosmic voids is how they might have affected the early universe. Shortly after the Big Bang, the universe was filled with hot gas and radiation. As it expanded and cooled, small variations in the density of matter formed the first galaxies and stars. Over time, the regions with less matter became the voids we see today. This process is known as cosmic evolution, and it has helped shape the universe over billions of years. Essentially, the voids were created as a byproduct of the way matter spread out after the Big Bang. In terms of the larger structure of the universe, cosmic voids also serve as markers for scientists studying the universe's expansion. By examining the size and distribution of voids, scientists can gain insights into how the universe has grown over time. For instance, voids may provide clues about the nature of dark energy, a mysterious force that seems to be driving the accelerated expansion of the universe. If dark energy is responsible for pushing galaxies apart, it could be affecting how voids are growing. Scientists are still studying this connection, using voids as a tool to understand the greater forces at work in the universe. Another key feature of voids is how they affect the light that travels through them. Because the matter in a cosmic void is so thin, there is very little to block or scatter light. This means that light can travel through these empty regions without much interference. When light from distant galaxies passes through a cosmic void, it can travel much further than it would in denser regions. This makes cosmic voids great for studying distant objects, as they provide a clear view of the universe beyond. Despite their emptiness, voids are far from meaningless. They are an essential part of the universe's overall structure. They help shape the cosmic web and influence how galaxies and other cosmic objects move and evolve over time. They also provide an opportunity for scientists to study some of the most fundamental questions about the universe, including the nature of dark energy and the early stages of cosmic evolution. By understanding voids, we gain a better understanding of the universe as a whole and how it has changed over billions of years. While they may seem like vast, empty spaces, cosmic voids are anything but barren. They are an active part of the universe's structure, and they play a role in shaping the galaxies and stars that populate the rest of space. Far from being empty, they are a critical piece of the cosmic puzzle that scientists continue to study and explore. Intergalactic space may seem empty, but it's not as void as it first appears. In fact, there's a mysterious substance hidden throughout this vast expanse, dark matter. Dark matter doesn't shine like stars or emit light, so it's invisible to us. Even though we can't see it directly, scientists believe it exists because of the way it interacts with visible matter, especially through gravity. Imagine walking through a completely dark room. You can't see anything, but you know there's something there because of how it affects the objects around it. For example, if you walk into a chair, you can tell it's there, even though you can't see it. This is similar to how scientists detect dark matter. It doesn't glow or give off any energy we can measure, but its presence is clear through the effects it has on the things we can see. One of the most significant effects is the way galaxies and galaxy clusters behave. Galaxies don't rotate the way we would expect them to based on the visible matter they contain. If you could only see the stars in a galaxy, you might think the outer stars should move more slowly, like the planets at the edge of our solar system, but they don't. Instead, they move much faster than they should. This strange behavior suggests there is something else, something invisible, exerting additional gravity, holding everything together. Scientists have named this invisible force dark matter. Dark matter also plays a crucial role in the structure of the universe. Without it, galaxies would fly apart. Its gravitational pull is what keeps galaxies bound together. Without it, there wouldn't be the large-scale structures we see today. In fact, dark matter acts like a cosmic glue that holds galaxies and galaxy clusters together. It helps form the large web-like structure of the universe. These webs consist of galaxies connected by long threads of dark matter and gas, stretching across vast distances. Despite being invisible, dark matter is everywhere. Scientists believe it makes up about 27% of the universe's total mass and energy. That's a huge portion of the universe. Yet it's something we can't see. The rest of the universe is made up of regular matter, the stuff that stars, planets, and galaxies are made of. But dark matter far outweighs the ordinary matter we see. It's one of the greatest mysteries in modern science, and we're still trying to understand what it is and how it works. The only way scientists have tried to understand dark matter is by looking at how galaxies move within clusters. A galaxy cluster is a large group of galaxies bound together by gravity. If you observe a galaxy cluster, you can see the galaxies moving around each other. However, there's not enough visible matter, such as stars and gas, to explain the way these galaxies move. The galaxies move as if there's much more mass present than what we can see. This unseen mass is believed to be dark matter, pulling on the galaxies with its gravity and holding the cluster together. Dark matter also affects light. When light passes through a galaxy cluster, it bends, just like how light bends when it passes through a magnifying glass. This bending is due to gravity, and it's called gravitational lensing. The amount of bending shows that there's more mass in the cluster than we can see with our eyes. This mass is thought to be dark matter. Scientists have observed this effect in many places, further confirming that dark matter exists and has a significant influence on the universe. It's important to note that dark matter doesn't interact with light or other forms of energy. This is why we can't see it directly. It doesn't absorb, reflect, or emit light, making it different from ordinary matter. However, it does interact with visible matter through gravity. For example, when dark matter passes near a galaxy, it can affect the galaxy's rotation or the way stars move within it. This gravitational interaction is what gives dark matter away. While dark matter is invisible, scientists have come up with a few theories about what it might be. One of the leading theories is that dark matter is made up of particles that are different from the particles that make up normal matter. These particles are called WIMPs, weakly interacting massive particles. WIMPs are thought to be heavy and interact only weakly with other particles. which is why we can't detect them directly. Another possibility is that dark matter could be made up of axions, tiny particles that are also difficult to detect. Despite all the theories, scientists haven't yet found direct evidence of what dark matter is made of. It remains a mystery. Another interesting aspect of dark matter is how it affects the growth and formation of galaxies. When the universe was very young, it was filled with hot gas and matter. Over time, gravity pulled matter together, forming the first stars and galaxies. Dark matter played a key role in this process. As matter gathered together, dark matter acted as a scaffolding, helping galaxies form and grow. Without dark matter, the universe might not have developed the way it did. Dark matter also helps explain some of the strange patterns scientists observe in the universe. For example, the way galaxies move relative to each other suggests that there's more mass out there than we can see. Dark matter is the missing piece of the puzzle, providing the extra gravity needed to explain these movements. Without dark matter, many of the things we observe in space, like galaxy rotations and gravitational lensing, wouldn't make sense. Despite its importance, dark matter is still a mystery. It doesn't emit light, and we can't detect it through traditional means. Scientists are working hard to uncover more about it, using a variety of methods. Some scientists are searching for direct evidence of dark matter particles in underground laboratories. Others are studying how dark matter affects galaxies and clusters of galaxies. By studying its effects, we can learn more about what dark matter is and how it influences the universe. Even though dark matter is invisible, its presence is undeniable. It holds galaxies together, helps form the structure of the universe, and influences the way objects move through space. While scientists still don't know exactly what dark matter is, it's clear that it's one of the most important components of the universe. It may be invisible to our eyes, but its impact is felt across the cosmos, shaping the universe in ways we're just beginning to understand. Cosmic microwave background radiation is one of the most important discoveries in the study of the universe. This faint radiation is a leftover signal from the Big Bang, the event that began the universe. It fills all of space, from the edges of our galaxy to the vast stretches of intergalactic space. Although it is invisible to the naked eye, scientists can detect it using special instruments. The cosmic microwave background, often shortened to CMB, provides us with a glimpse into the early stages of the universe. To understand why this radiation is so important, we need to go back to the beginning of everything. Around 13.8 billion years ago, the universe began with the Big Bang. In those early moments, the universe was incredibly hot and dense. Over time, it expanded, cooling as it grew. As the universe cooled, atoms began to form, and light could finally travel freely through space. This light, or radiation, is what we now detect as the CMB. It is the oldest light in the universe, a remnant of the very first moments after the Big Bang. The CMB is a kind of afterglow, like the faint light you might see after a flash of lightning. But unlike the light from a lightning bolt, the CMB has been traveling through space for billions of years. As it moved, it stretched out, shifting toward longer wavelengths. This is why we now observe it as microwave radiation. The radiation is evenly spread throughout the universe, filling every corner of space. Scientists first discovered the CMB in 1965. They were not looking for it when they found it. Two radio engineers, Arno Penzias and Robert Wilson, were trying to study radio signals from the sky when they came across a strange noise that seemed to come from everywhere. This noise was constant, and it didn't change or disappear. After ruling out other possible sources, they realized they had detected the CMB, the faint radiation left over from the Big Bang. This discovery was a key piece of evidence that supported the Big Bang theory, showing that the universe had a beginning and has been expanding ever since. The CMB is not just a faint noise, it carries vital information about the early universe. Because it comes from a time when the universe was just 380,000 years old, it acts as a snapshot of the universe in its infancy. The patterns in the CMB give scientists clues about what the universe was like at that time. For example, the temperature fluctuations in the CMB show areas where the density of matter was higher or lower. These differences eventually led to the formation of galaxies, stars, and other structures. Think of the CMB as a kind of map by studying it. Scientists can trace how the universe expanded and changed over billions of years. The small variations in temperature that we observe in the CMB are like footprints from the early universe, providing a record of how matter and energy were distributed. These variations are incredibly important because they allow scientists to test different models of the universe's evolution. They help us understand the rate of expansion, the amount of dark matter, and other key aspects of the universe's history. The CMB is not just important for understanding the past. It also gives us insight into the future. By studying how the radiation has changed over time, scientists can make predictions about how the universe will continue to evolve. For example, the CMB gives us a better idea of the overall shape and structure of the universe. It shows that the universe is flat, meaning that on the largest scales, the geometry of space is not curved. This is a crucial piece of the puzzle when trying to understand how the universe behaves on the grandest scales. One of the most fascinating aspects of the CMB is how it connects to the expansion of the universe. As the universe has expanded, the CMB radiation has been stretched, changing its wavelength from the visible light of the early universe to the microwave radiation we detect today. This stretching, known as redshift, happens because the universe is still expanding. The CMB, in a sense, carries with it a record of that expansion. By studying how much the radiation has stretched, scientists can calculate how fast the universe is expanding. This is important because understanding the rate of expansion helps us understand the fate of the universe. If the universe continues to expand forever, it could eventually reach a point where all the stars burn out and galaxies drift apart. Alternatively, if the expansion slows down and reverses, the universe might eventually collapse back in on itself. The CMB gives scientists the data they need to make predictions about these possibilities. The study of the CMB has also led to some of the most profound discoveries in modern cosmology. For example, one of the biggest surprises came from studying the patterns in the CMB in detail. Scientists found evidence for a concept called inflation. Inflation theory suggests that in the very early universe, there was a period of rapid expansion, much faster than the speed of light. This rapid growth smoothed out the universe and set the stage for the structure we see today. The patterns in the CMB provide indirect evidence for inflation, and this finding has been one of the most exciting breakthroughs in understanding the early universe. To detect the CMB, scientists use telescopes and specialized instruments that are designed to pick up microwave radiation. These telescopes are placed in space above the Earth's atmosphere, because the atmosphere can block out the signals. The most famous of these telescopes is the Planck satellite, which operated from 2009 to 2013. Planck provided the most detailed map of the CMB ever created, allowing scientists to study the universe's early history with remarkable precision. The CMB is not just a faint signal from the past. It continues to be a tool that helps us explore the deepest questions about the universe. Every time scientists analyze the radiation, they learn more about how the universe began, how it has evolved, and where it might be headed in the future. The CMB is one of the most valuable pieces of information we have, a signal from the earliest moments of the universe that still resonates today. It's easy to overlook something as faint as the cosmic microwave background radiation, But when you stop and consider its significance, it becomes clear how much it tells us. This radiation is a direct link to the universe's past, offering clues to the mysteries of the Big Bang and the forces that have shaped the cosmos. The CMB is not just a leftover signal, it's a treasure trove of information, helping us piece together the story of everything. Even in the farthest reaches of intergalactic space, where stars and galaxies are spread thinly, large-scale magnetic fields are believed to exist. These fields stretch across vast areas of space, much like invisible threads connecting distant cosmic objects. Despite their apparent influence, scientists still do not fully understand their exact nature or the role they play in the universe's larger structure. They are, however, crucial to our understanding of space, from the formation of galaxies to the movement of cosmic particles. Magnetic fields are created by moving electric charges, like those in the atoms of matter. On Earth, we experience magnetic fields through the north and south poles of a magnet, or the Earth's own magnetic field. These fields influence the way particles move and can even protect our planet from harmful cosmic radiation. In space, magnetic fields also exist, but on a much larger scale. Instead of being confined to a small area like a magnet on a refrigerator, the magnetic fields in space stretch across entire galaxies and beyond. One example of a large-scale magnetic field is the one surrounding our own galaxy, the Milky Way. The magnetic field of the Milky Way is thought to stretch across the entire galaxy, affecting everything from the movement of charged particles to the formation of stars. But beyond our galaxy, there are also magnetic fields that stretch through the intergalactic space between galaxies. These fields are not directly tied to any particular star or galaxy, but rather appear to form a cosmic web, influencing the motion of galaxies and the particles within them. Even though these magnetic fields are believed to be large and powerful, they are not easy to study. The difficulty lies in their vast scale, and the fact that they do not emit light or any other easily detectable signals. Most of our understanding comes from observing their indirect effects. For example, we can see how magnetic fields influence the movement of charged particles, like electrons and protons. When these particles travel through space, they move along the lines of magnetic fields, creating patterns that we can observe. These patterns help scientists map out where the magnetic fields are and how they affect the surrounding space. One of the most visible effects of large-scale magnetic fields is the way they shape the behavior of plasma, the fourth state of matter that makes up much of the universe. Plasma consists of charged particles like electrons and ions, and magnetic fields have a powerful influence on it. In galaxies, magnetic fields help regulate the movement of plasma in their gas clouds. In intergalactic space, magnetic fields can affect the movement of plasma between galaxies, possibly even helping to shape the formation of galaxies and clusters of galaxies. Scientists also believe that magnetic fields play a role in the acceleration of cosmic particles, such as cosmic rays. These high-energy particles travel through space at incredible speeds, and magnetic fields can alter their paths. This is particularly important in areas like galaxy clusters, where large magnetic fields might guide the motion of cosmic rays and other particles. Understanding how these fields interact with cosmic particles can help scientists understand the behavior of matter at the edges of galaxies and even in the empty spaces between them. Another key area where magnetic fields are important is in the study of galaxy clusters. Galaxy clusters are enormous groups of galaxies that are bound together by gravity. Within these clusters, magnetic fields are thought to be widespread. They help organize the motion of charged particles, influencing everything from the temperature of the gas within the clusters to the behavior of the galaxies themselves. Magnetic fields may also play a role in the mysterious phenomenon of cosmic radio emissions. In some galaxy clusters, scientists have observed strange, powerful radio waves. These waves are believed to be generated by magnetic fields, showing just how much influence these fields have over the matter in space. Yet, despite all these observations, scientists still don't fully understand the properties of these magnetic fields. The exact way they form, the strength they can reach, and the full extent of their effects are still subjects of ongoing research. One of the most puzzling questions is how these fields persist over such vast distances. Magnetic fields in galaxies are often tied to specific sources, like a rotating star or the movement of gas. But in the case of intergalactic space, there is no obvious source for the magnetic fields. It's unclear how they are generated or maintained, and why they extend so far beyond the boundaries of individual galaxies. Researchers are working to answer these questions through various methods. Some scientists study the behavior of plasma and cosmic particles in space, looking for clues about how magnetic fields might shape their motion. Others use sophisticated telescopes that can detect the faint emissions caused by magnetic fields, even in the empty space between galaxies. These observations help build a clearer picture of the magnetic environment in intergalactic space, even if many details remain unknown. Magnetic fields also play an important role in understanding the broader structure of the universe. The distribution of galaxies and the cosmic web are shaped in part by the forces of magnetism. If magnetic fields are indeed as widespread as scientists believe, they may be part of the unseen framework that connects galaxies and galaxy clusters across vast stretches of space. This cosmic web, formed by the interplay of gravity, dark matter, and magnetic fields, is one of the key structures that shapes the universe. As we study more distant parts of space, we find that the effects of magnetic fields become more significant. For instance, in the far reaches of intergalactic space, far from the influence of any galaxy or star, the magnetic fields still seem to persist. Their presence suggests that they are not just the byproducts of nearby galaxies, but a part of a much larger, more universal system. These fields may help explain how matter moves and behaves across the vast distances between galaxies. Magnetic fields in space may also help us understand other cosmic mysteries, such as dark matter and dark energy. These invisible forces make up most of the universe's mass and energy, yet we know little about them. By studying how magnetic fields interact with visible matter and how they shape the cosmic web, scientists may uncover new insights into the nature of dark matter and dark energy. It's possible that these fields have a deeper connection to the forces that govern the universe, though how exactly this relationship works is still unclear. In the end, while magnetic fields are not visible to the naked eye, their influence is undeniable. They stretch across vast regions of space, shaping the way galaxies, gas clouds, and particles move. From the smallest scales inside galaxies to the largest structures in the universe, magnetic fields help organize and guide the flow of matter. Though much about their properties remains unknown, magnetic fields are one of the most important factors in understanding how the universe operates, from the edges of intergalactic space to the heart of galaxies. The space between galaxies, known as intergalactic space, is not completely empty. It's filled with a very thin yet important substance called the intergalactic medium, EIM. The IgM is made up mostly of ionized hydrogen, the simplest element in the universe, along with trace amounts of other elements such as helium and a few heavier atoms. Despite being spread out across vast stretches of space, the IgM plays a key role in how the universe works. The IgM is made up of very low-density gas. If you could somehow travel through this region, you wouldn't notice much. The particles are so spread out that, in many ways, it's like walking through an almost perfect vacuum. Imagine walking through a room filled with only a few tiny dust particles scattered around. The air would seem almost empty, but those few particles are still there, affecting the space around them. The IgM is similar. There are very few particles per cubic meter, but it still has an impact on the universe. One of the most common components of the IgM is ionized hydrogen. Hydrogen is the most abundant element in the universe, and it forms the building block of many stars, planets, and galaxies. In the IgM, the hydrogen atoms are often stripped of their electrons, turning them into positively charged ions. This ionization happens because of the intense radiation from stars and galaxies, which breaks the hydrogen atoms apart. Even though this gas is spread thin, its properties can still be detected through the light that passes through it. The way light is absorbed and scattered as it moves through the IgM gives scientists important clues about its makeup and behavior. The IgM is not just a passive background feature of space. It actively interacts with the objects in the universe. For example, when light from distant stars or galaxies travels through the IgM, some of it is absorbed by the ionized hydrogen. This absorption can leave a telltale signature in the light spectrum, helping scientists study the IgM's properties. The IgM also affects the movement of galaxies and clusters of galaxies. The gas in the IgM can create drag, slowing down the motion of galaxies as they move through it. This is part of a larger process called the cosmic web, a network of galaxies and gas that stretches across the universe. Even though the IgM is made up of very sparse gas, it has a significant effect on the universe's structure. For example, it can help shape the formation of galaxies and the way galaxies interact with each other. When galaxies collide or merge, the gas from the IgM can influence how they behave. This interaction can trigger the formation of new stars, or even change the shape of existing galaxies. The IgM's role in galaxy formation and evolution is one of the key areas scientists are trying to understand. In galaxy clusters, where many galaxies are closely packed together, the IgM becomes more noticeable. The gas in these clusters is much denser than in the empty space between galaxies. It acts like a hot, diffuse cloud that surrounds the galaxies, creating an environment that can influence how galaxies move and interact with each other. This gas in galaxy clusters is often so hot that it emits X-rays, which scientists can detect using space telescopes. These X-rays help scientists learn about the temperature and density of the IgM in clusters, providing more information about the forces at work in these regions. Despite the low density of the IgM, it plays a significant role in the evolution of the universe. It is often the medium through which galaxies grow and evolve. When new stars form, they can release energy and heat into the surrounding gas in the IgM. This can trigger the formation of more stars as the gas gets heated and compressed. The IgM can also play a role in how galaxies maintain their shape over time. Without the IgM, galaxies might not be able to sustain themselves or grow in the way they do. Scientists are still working to understand the full scope of the IgM's influence. One of the biggest questions is how the gas in the IgM behaves over time. Because it is so diffuse, it can be hard to measure. However, by studying the light from distant galaxies and using advanced telescopes, scientists are starting to get a better picture of the IgM's properties. They are learning more about the temperature, density, and chemical composition of the gas, as well as how it moves and interacts with other parts of the universe. In addition to ionized hydrogen, the IgM contains small amounts of other elements, including helium, carbon, and oxygen. These elements are created in stars and supernova explosions, and they are spread out through the universe. The amount of these heavier elements in the IgM can tell scientists about the history of star formation and the life cycle of galaxies. For example, when stars explode as supernovae, they release heavy elements into the surrounding gas, enriching the IgM. Studying the presence of these elements helps scientists understand how galaxies and stars evolve over time. Despite being so spread out, the IgM is an essential part of the cosmic ecosystem. It connects the various components of the universe, from galaxies to clusters of galaxies, to the vast empty space in between. The gas in the IgM acts as a bridge, helping to transfer energy, matter, and momentum across great distances. Without the IgM, the universe would be a very different place. One of the more puzzling aspects of the IgM is its temperature. While the gas in the IgM is very thin, It is also incredibly hot, often reaching millions of degrees. This temperature is the result of the energy from stars, supernovae, and other cosmic events. The heat causes the gas to be in a state of constant motion, with particles moving at extremely high speeds. Despite the high temperature, the low density of the gas means that it doesn't feel hot in the way we experience heat on Earth. The heat in the IGM is more like the warmth of the sun on a clear day, felt over a vast distance, but not overwhelming. The IGM also plays a role in how galaxies are observed from Earth. Because it is spread out across space, it can affect the light that travels through it, sometimes altering the way we view distant galaxies. As light from distant stars and galaxies travels through the IGM, it can be absorbed or scattered by the gas. This can change the way galaxies appear to us, making them look dimmer or altering their color. Studying how light is affected by the IGM helps scientists learn about its properties and its role in the universe. Though the IGM is incredibly sparse and difficult to study, it has a major impact on the universe's structure and evolution. It influences the formation and movement of galaxies, and its presence helps define the large-scale structure of the universe. Even though the gas in the IGM is invisible to the naked eye, it is a vital component of the cosmos, and scientists are continuing to study it in order to understand more about how the universe works. Galaxies are not scattered randomly through space. Instead, they are organized into large-scale structures known as filaments, which form a cosmic web. These filaments are vast thread-like formations made up of galaxies, gas, and dark matter. The edges of intergalactic space, where there are fewer galaxies, often lie between these filaments. In what's known as voids, understanding these filaments helps scientists learn more about the overall structure of the universe and how galaxies are connected across vast distances. Imagine looking at a spider's web. The strands of the web are long, thin threads, and the points where they meet are the focal points of the structure. In a similar way, the universe's cosmic web consists of long, interconnected filaments of galaxies, with vast, empty voids in between. These filaments stretch across billions of light years and form the backbone of the universe's large-scale structure. Just as a spider's web holds together the space within its threads, the cosmic filaments hold together galaxies, dark matter, and gas, shaping the way the universe has evolved. The filaments are made up mostly of dark matter, a mysterious substance that cannot be seen directly, but whose presence is inferred from its gravitational effects. Dark matter doesn't emit light or energy, yet it plays a crucial role in the formation and structure of these filaments. In addition to dark matter, these filaments contain gas, much of it in the form of ionized hydrogen, and of course galaxies. Galaxies within the filaments are bound together by gravity, forming vast cosmic chains or webs that connect different clusters of galaxies across great distances. Think of the Milky Way galaxy, which is part of a larger cluster of galaxies. The Milky Way and its neighbors aren't just floating around in isolation. They are part of a much larger structure that stretches across the universe. This structure is the cosmic web, and the filaments are its defining feature. When viewed on a very large scale, these filaments look like a vast network of threads or strands, with galaxies lining the paths between them. In between these filaments, there are large empty regions called voids, where galaxies are far less common. This arrangement isn't random. The structure of the cosmic web is a result of the way gravity has acted over billions of years. Shortly after the Big Bang, matter in the universe was spread out evenly. Over time, however, slight variations in the density of matter caused areas of space to become slightly denser than others. These denser areas attracted more matter, creating the first small clusters of galaxies. As more time passed, Gravity pulled these clusters together into larger structures. The result is the cosmic web of galaxies connected by long, narrow filaments of dark matter and gas. The filaments themselves are often made up of gas that has been heated by the energy from stars and galaxies. This hot gas is known as the intergalactic medium. As galaxies move through the filaments, they can interact with this gas, exchanging energy, and helping to shape the evolution of the galaxies themselves. In fact, the gas in the filaments plays a role in how galaxies form and grow. The gas can be pulled into galaxies, fueling the birth of new stars, while also providing the raw materials for future galaxy formation. Galaxies within the filaments don't just sit still. They move through the cosmic web, influenced by the gravity of nearby galaxies and dark matter. This movement helps shape the overall structure of the universe. The filaments are not rigid. They are dynamic, with galaxies constantly moving along them, interacting with each other, and merging to form larger galaxies. These movements are part of the broader cosmic dance that has been happening since the beginning of time. The filaments also help explain some of the mysteries of the universe. For example, they provide clues about the nature of dark matter. Dark matter cannot be seen directly, but scientists know it exists because of its gravitational effects. By studying the way galaxies move within the filaments, scientists can learn more about how dark matter behaves and how it shapes the universe. Dark matter is thought to form the framework of the filaments, with galaxies and gas filling in the spaces between the threads. The edges of intergalactic space, where there are fewer galaxies, lie between these filaments. These regions, known as cosmic voids, are vast stretches of space where the density of galaxies is extremely low. While the filaments are dense with galaxies and dark matter, the voids are essentially empty. These voids can be hundreds of millions of light years across, and they provide a striking contrast to the densely packed filaments. The existence of these voids is one of the defining features of the cosmic web. Even though these voids are largely empty, they are not completely devoid of matter. They still contain a small amount of dark matter and gas, though the density of both is much lower than in the filaments. The voids are important because they provide a kind of negative space in the cosmic web, helping to define the structure of the universe. By studying the voids, scientists can learn more about the distribution of matter in the universe and how it has evolved over time. One of the key features of the cosmic web is its scale. The filaments are some of the largest structures in the universe. They stretch across vast distances, linking galaxies and galaxy clusters in a giant network. To give a sense of just how big these structures are, consider that the filaments are often hundreds of millions of light years long. A light year is the distance that light travels in 1 year, about 5.88 trillion miles. So when you think about the scale of the cosmic filaments, it becomes clear just how massive these structures are. Even though the filaments themselves are incredibly vast, the galaxies within them are still relatively close to one another, at least in cosmic terms. The galaxies are connected by the dark matter and gas that make up the filaments, which form a sort of cosmic highway. Over billions of years, these filaments have helped guide the movement of galaxies and shape the way they interact with each other. The gravitational pull of the filaments can even cause galaxies to fall toward each other, eventually leading to collisions and mergers. The cosmic web is a stunning example of how the universe is organized. Far from being a random scattering of stars and galaxies, the universe has a complex, interconnected structure. The filaments are the highways that connect galaxies across vast distances, and the voids are the empty spaces in between. Together, they form a web that stretches across the entire universe. This structure not only shapes the way galaxies move and interact, but also offers important clues about the nature of dark matter, the forces that govern the cosmos, and the way the universe has evolved over billions of years. The edge of intergalactic space, marks the furthest point we can observe in the universe. And this boundary is a result of a process known as cosmic inflation. Cosmic inflation describes an incredibly rapid expansion that occurred just after the Big Bang. It was a brief period in the early universe, when everything grew exponentially faster than the speed of light. This expansion set the stage for the universe, as we know it today, influencing the way galaxies, stars, and planets formed and ultimately shaping the observable universe. To understand cosmic inflation, it's helpful to picture the universe like a balloon. Imagine you have a tiny balloon, and as you blow air into it, it quickly expands in all directions. In the early moments of the universe, space itself was expanding, and this inflationary period stretched space faster than anything could travel within it, including light. This rapid expansion occurred within a fraction of a second, meaning that regions of the universe that were once very close together were suddenly pushed far apart. The result was a smooth and even distribution of matter and energy, which created the foundation for the universe's large-scale structure. Before cosmic inflation, the universe was a hot, dense soup of particles and radiation. In this early state, the universe was too small and too crowded for anything to form as we know it today. But then, inflation took over. Within an incredibly short time, less than a trillionth of a second, the universe expanded by a factor of more than 1 trillion times. This sudden growth smoothed out any irregularities, setting up the universe for the later formation of galaxies and stars. After inflation ended, the universe continued to expand, but at a much slower rate, and eventually the first particles formed, giving rise to atoms and, later, galaxies. The observable universe is the region of space we can see from Earth. It's limited by how far light has been able to travel since the Big Bang. Since light moves at a finite speed, the farthest light we can see has traveled for about 13.8 billion years. However, the actual size of the universe is much larger, possibly infinite. The edge of the observable universe is determined by the amount of time light has had to reach us since the beginning of time. But it's important to note that this edge is not a hard boundary. It is simply the limit of what we can observe. The universe itself extends far beyond this, and its size may be much larger than what we can see. The inflationary period played a critical role in shaping the observable universe. Before inflation, the universe was incredibly small and incredibly hot. After inflation, the universe expanded rapidly, causing the matter that was once very close together to spread out. This helped to establish the uniformity we observe today. The process also set the stage for the formation of galaxies and clusters of galaxies. Even though inflation occurred only in the earliest moments of the universe, its effects are still present today in the way galaxies are distributed and in the cosmic background radiation that fills the universe. This background radiation, known as the cosmic microwave background, CMB, is a key piece of evidence supporting the theory of cosmic inflation. The CMB is a faint glow that fills the universe, and it is a remnant of the heat left over from the Big Bang. When inflation happened, it stretched the universe so rapidly that it spread the energy out evenly. This uniform distribution is evident in the CMB. Tiny fluctuations in temperature and density in the CMB are the imprints of the tiny variations that existed in the universe before inflation. These small fluctuations later grew into the galaxies, stars, and clusters we observe today. One of the remarkable things about cosmic inflation is that it not only explains the large-scale structure of the universe, but also why the universe appears so uniform. If inflation had not occurred, the universe would likely look much more uneven, with large patches of dense matter and other areas that were emptier. But because of the rapid expansion, the universe became more uniform, and galaxies were able to form in a smoother and more predictable manner. This uniformity also explains why the observable universe looks roughly the same in every direction we look, while cosmic inflation is a key part of the story of the universe's early history. It also raises some interesting questions. For example, if the universe expanded faster than light, doesn't that violate the rules of physics? The answer lies in understanding that space itself was stretching. It wasn't that anything inside the universe was moving faster than light. Rather, space itself was expanding at an incredible rate. This means that regions of space that were once in close contact with one another were suddenly moved far apart, but nothing was actually breaking the speed limit of light. The effects of inflation are still visible in the universe today. After inflation ended, the universe continued to expand, but at a slower pace. Over time, matter began to clump together under the influence of gravity, forming galaxies and other structures. Today, galaxies are arranged in vast clusters and filaments, creating the cosmic web. The way these structures formed, and the way the universe continues to expand, is all influenced by the rapid growth during inflation. Understanding inflation helps scientists predict how the universe will continue to evolve in the future. One of the major challenges with studying cosmic inflation is that it happened so quickly and so early in the universe's history. The events that took place during inflation were incredibly brief, lasting only a tiny fraction of a second. As a result, there is little direct evidence of this period, and much of what we know about it comes from mathematical models and observations of the current universe. The CMB, along with other cosmic phenomena, provides indirect evidence of inflation. But there's still much to learn about the specifics of how and why it happened. Cosmic inflation also has an important connection to the concept of the multiverse. Some versions of inflation theory suggest that the rapid expansion may not have happened just once, but could have occurred in different regions of space at different times. This idea leads to the possibility that there are multiple, separate universes, each with its own set of physical laws and conditions. While this is still a speculative idea, it's one of the fascinating implications of the theory of inflation. Ultimately, the edge of intergalactic space represents the limits of what we can observe, but it is not the true boundary of the universe. That boundary is defined by the vast expanse of space that continues beyond our ability to see. The expansion that took place during cosmic inflation set the stage for the universe we observe today, helping to explain the uniformity and structure of the cosmos. Even though inflation happened long ago, its effects continue to shape the universe, influencing the way galaxies form and the way light travels through space. It's one of the most important events in the history of the universe, and it has left an enduring imprint on everything we observe. Gravitational effects are felt throughout the universe, even in the farthest reaches of intergalactic space, even at the edges of galaxies where space seems empty and distant. The gravitational pull from nearby galaxies, clusters, and other cosmic structures still plays a role. These effects, although subtle, shape the movement of galaxies, the distribution of matter, and the structure of the universe itself. The pull of gravity extends far beyond the boundaries of individual galaxies and clusters, influencing the vast stretches of intergalactic space. In space, gravity is the force that keeps planets in orbit around stars, stars in orbit around the centers of galaxies, and galaxies moving in relation to one another. Gravity works by pulling objects toward each other, and this pull is always present, no matter how far apart the objects are. However, the strength of gravity weakens with distance, so objects at the edges of galaxies or in deep intergalactic space experience much weaker gravitational forces than those near massive objects like stars or black holes. Even though the gravitational pull at the edges of galaxies is weak compared to the strong forces at the center, it still has a significant influence. Galaxies do not exist in isolation. They are part of a much larger cosmic network. Galaxies are bound together into clusters, and these clusters, in turn, are part of an even larger structure called the cosmic web. The cosmic web is made up of vast strands of galaxies and dark matter, connected by long filaments and separated by large voids. The gravitational influence of nearby galaxies and clusters can cause galaxies to move, interact, and even collide over time. At the outer edges of a galaxy, where stars are less densely packed, the gravitational pull from other galaxies and nearby cosmic structures can still affect the motion of stars and gas. For example, a galaxy that is part of a cluster might feel the gravitational influence of its neighboring galaxies. These gravitational interactions can cause stars in the galaxy to move slightly differently than they would if the galaxy were isolated. In some cases, this influence can even lead to the stretching or bending of the galaxy's shape, especially when galaxies interact or collide with one another. One of the most important gravitational effects in intergalactic space is the way galaxies move within clusters. Galaxies within a cluster are held together by gravity. The stronger the cluster's gravity, the more galaxies will be drawn toward the center of the cluster. This effect, known as gravitational attraction, shapes the overall structure of the cluster, and it also plays a role in how galaxies within the cluster evolve over time. When galaxies move through a cluster, they can be affected by the gravitational forces of the other galaxies, leading to interactions such as galaxy mergers or the exchange of gas and stars between galaxies. These gravitational interactions can have a lasting effect on galaxies, even at the outermost edges. For example, when two galaxies pass close to each other, their gravitational pull can distort each other's shape, causing the galaxies to stretch or even trigger bursts of star formation. Over time, this can lead to the merging of galaxies, where two or more galaxies collide and combine into a single larger galaxy. This process, known as a galactic merger, is common in galaxy clusters, where galaxies are tightly packed and more likely to interact with one another. Even in the vast stretches of intergalactic space, gravity can still affect the motion of galaxies. The gravitational pull of massive galaxy clusters can cause galaxies outside the cluster to move toward the cluster. This movement is a key part of the way galaxies are arranged in the universe. Some galaxies, known as satellite galaxies, are gravitationally bound to larger galaxies. These smaller galaxies orbit their larger neighbors, slowly moving closer over time. This movement is the result of the gravitational forces at play within the cosmic web. The influence of gravity is not limited to galaxies and clusters. It also affects the distribution of gas and dark matter in intergalactic space. Dark matter, which makes up much of the mass in the universe, is invisible but detectable because of its gravitational pull. It does not emit light, but it has mass, and therefore exerts gravity. Dark matter is thought to be concentrated in the filaments that connect galaxies and clusters, providing the underlying structure of the cosmic web. The gravitational pull of dark matter helps hold galaxies together and influences their motion. In intergalactic space, the gravity of dark matter also affects the movement of gas. Gas that is spread out between galaxies can be pulled toward areas of higher gravity, such as the regions around galaxy clusters. This gas can then be compressed and heated, contributing to the formation of new stars, or fueling the growth of existing galaxies. The gas in intergalactic space is not static. It moves in response to the gravitational forces acting on it. This movement can be subtle, but over billions of years, it shapes the structure and evolution of the universe. In some cases, the gravitational pull of distant galaxies or clusters can also bend the path of light. This phenomenon, known as gravitational lensing, occurs when the gravity of a massive object causes the light from a more distant object to bend as it passes by. This bending of light can magnify and distort the image of the distant object, allowing scientists to study galaxies and other cosmic structures that would otherwise be too faint or far away to observe. Gravitational lensing provides important insights into the distribution of matter in the universe. including dark matter, which does not emit light but can still influence the path of light. The effects of gravity in intergalactic space also have an impact on the overall structure of the universe. The way galaxies are distributed, the way they move within clusters, and the way matter is spread throughout the cosmic web are all shaped by gravity. Gravity is the force that pulls galaxies and clusters together. Without gravity, the universe would be a very different place, with galaxies scattered randomly throughout space and no large-scale structure to hold everything together. The gravitational effects in intergalactic space are not limited to galaxies and clusters. They also influence the behavior of the universe on the grandest scales. For example, the expansion of the universe itself is influenced by gravity. Although the universe has been expanding since the Big Bang, gravity works to slow down the expansion, pulling galaxies and clusters together. Over time, this has led to the formation of the large-scale structure of the universe that we see today. Even at the edges of galaxies and across the vast stretches of intergalactic space, gravity continues to have an effect. The gravitational pull from nearby galaxies, clusters, and other cosmic structures may be subtle, but it shapes the motion of galaxies, the distribution of matter, and the overall structure of the universe. The invisible force of gravity binds the universe together, influencing everything from the movement of stars to the growth of galaxy clusters. And it helps explain the large-scale structure of the cosmos. At the heart of many galaxies lies a supermassive black hole, a mysterious object with an enormous gravitational pull. These black holes are not just isolated features confined to the centers of galaxies. Their influence stretches far beyond, affecting not only the galaxy they inhabit, but also the surrounding regions of space, even reaching into the edges of intergalactic space. The gravitational forces and radiation emitted by these black holes extend through vast distances, impacting the structure and behavior of the universe itself. A black hole is an area of space where gravity is so intense that nothing, not even light, can escape from it. Supermassive black holes, which are millions to billions of times the mass of the Sun, are found at the centers of most large galaxies, including our own Milky Way. The gravitational pull of these black holes is immense, and as matter falls toward them, it generates significant energy in the form of radiation. This radiation is so powerful that it can influence the environment of the galaxy and beyond, affecting the behavior of stars, gas clouds, and even entire galaxies. Zone of the ways supermassive black holes affect their surroundings is through the process of accretion. As matter, such as gas, dust, or even stars, gets drawn toward a black hole, it forms a spinning disk of material around it, known as an accretion disk. As the material in this disk spirals closer to the black hole, it heats up, emitting intense radiation, including X-rays and other forms of light. This radiation can have a far-reaching effect, blasting through the surrounding space and impacting neighboring regions. The radiation from a supermassive black hole can even influence the gas between galaxies, affecting the intergalactic medium. The intense radiation generated by black holes doesn't just affect the immediate area around them. It can extend well beyond the galaxy into the vast stretches of intergalactic space. When matter is pulled into a black hole, it doesn't always fall smoothly. Sometimes the black hole can shoot out powerful jets of particles and radiation, a phenomenon known as relativistic jets. These jets can travel at nearly the speed of light and stretch across vast distances, potentially reaching well beyond the galaxy's edge. These jets can impact the gas and matter between galaxies, influencing the structure of the intergalactic medium and the dynamics of galaxies in the cluster. Even though black holes are incredibly far away from one another in the vastness of space, their gravitational pull still has an effect. Gravity, as a force, extends across infinite distances, though it weakens as it spreads out. Supermassive black holes at the centers of galaxies exert a strong gravitational pull on the stars and gas within their own galaxy. But the influence of gravity can extend beyond the galaxy, subtly affecting nearby galaxies in the same cluster. The gravitational influence of black holes in one galaxy can cause the galaxies around them to move, sometimes altering their orbits within the cluster. This is especially noticeable in galaxy clusters, where the combined gravitational pull of many black holes can affect the movement of galaxies within the cluster. The presence of black holes at the centers of galaxies also plays a key role in shaping the overall evolution of galaxies. As a black hole grows and consumes matter, it can release vast amounts of energy. This energy can be carried outwards, affecting the surrounding gas clouds and star formation. In some cases, the energy released by a supermassive black hole can slow or even halt star formation within its galaxy. This happens when the radiation from the black hole heats up the surrounding gas, preventing it from cooling down and condensing into new stars. In this way, the presence of a black hole can shape the future of its galaxy, influencing the rate at which new stars are born. In addition to the radiation, the gravitational pull of a supermassive black hole can also affect the orbits of nearby stars. The black hole's gravity can cause stars to move in ways that they otherwise would not, creating strange orbits and sometimes leading to the collision of stars or the stripping of stars from their galaxies. These interactions can lead to the formation of star clusters, or they can cause stars to be flung out into intergalactic space. The influence of supermassive black holes on their galaxies is not limited to radiation and gravity alone. Black holes can also affect the formation and growth of galaxies over time. For example, in the early stages of the universe, when galaxies were first forming, supermassive black holes may have played a role in regulating the rate of star formation. In some galaxies, the energy and radiation from a black hole could prevent too much gas from collapsing and forming stars. In other cases, the black hole's growth could stimulate the formation of new stars by compressing gas in the galaxy's center. The black hole thus acts as a key factor in the galaxy's life cycle, helping to control how the galaxy evolves and how many stars it can produce. Beyond individual galaxies, the gravitational pull of supermassive black holes can influence the larger structures of the universe. In clusters of galaxies, for example, the combined gravitational forces of the black holes can cause galaxies to move and interact in complex ways. Some of these interactions can lead to galaxy mergers, which can alter the properties of the galaxies involved and even trigger the formation of new black holes. These mergers can also send shock waves through the surrounding space, compressing gas and triggering bursts of star formation. As galaxies collide and merge, they create new structures, all of which are influenced by the gravitational and energetic effects of the supermassive black holes at their centers. In regions far from any galaxies, in the edges of intergalactic space, the gravitational influence of these black holes can still be detected. While the force of gravity weakens with distance, the cumulative gravitational pull of many galaxies, each with its own black hole at the center, can create a noticeable effect on the movement of galaxies in clusters. This gravitational pull can influence the way galaxies are arranged and how they move through the universe. Over billions of years, the combined gravitational effects of black holes have helped to shape the large-scale structure of the universe. Furthermore, the intense radiation from supermassive black holes can also affect the surrounding intergalactic medium. As black holes release energy, they can heat the gas between galaxies, preventing it from cooling and condensing into new stars. This process can slow the growth of galaxies and influence the evolution of the larger cosmic structures. The radiation emitted by black holes also affects the cosmic web, the vast network of galaxies and dark matter that connects galaxies across the universe. In this way, black holes play a role in shaping the evolution of the entire universe. In summary, supermassive black holes are far more than just cosmic oddities at the centers of galaxies. Their influence stretches far beyond their immediate surroundings, affecting galaxies, clusters of galaxies, and even the empty regions of intergalactic space. Through their immense gravitational pull and the radiation they emit, supermassive black holes help shape the structure and evolution of the universe. From the formation of stars and galaxies to the movement of cosmic matter across vast distances. Cosmic rays are high, energy particles that travel through space at incredible speeds, often originating from the farthest reaches of the universe. These particles, which include protons, electrons, and atomic nuclei, can have energies millions of times greater than those created in particle accelerators here on Earth. Many of these cosmic rays come from deep intergalactic space, traveling vast distances from distant galaxies or even the outskirts of black holes. They carry immense amounts of energy, and their journey across space is a key part of the broader cosmic environment. Imagine a particle racing through space, moving faster than a bullet shot from a gun, and yet still carrying energy far beyond what we experience in our everyday world. These particles are cosmic rays, and they don't just stay within the confines of a galaxy or solar system. They can travel through the vast emptiness of space, across billions of light years, until they finally reach Earth, where they can sometimes be detected by sensitive instruments. Though we can't see them with our eyes, cosmic rays play an important role in shaping the universe and influencing everything from the behavior of galaxies to the conditions in our own solar system. Cosmic rays are thought to originate from extreme events in the universe, such as exploding stars, supernovae, active regions around black holes, and the highly energetic environments found in distant galaxies. These events send high-energy particles speeding outward into space. For example, when a star explodes in a supernova, it releases an enormous amount of energy which can accelerate particles to near the speed of light. The shock waves from these explosions can send cosmic rays into intergalactic space, where they continue traveling across vast distances. Some of the most powerful cosmic rays are believed to come from the areas around supermassive black holes. These black holes, found at the centers of most large galaxies, have gravitational pulls so strong that they can accelerate particles to extreme speeds. As matter falls into a black hole, it can create intense radiation and powerful jets of particles. These jets, which shoot out from the black hole at nearly the speed of light, can carry high-energy particles far into intergalactic space. These particles can travel across millions of light years, reaching us here on Earth. What makes cosmic rays particularly interesting is the amount of energy they carry. For comparison, the most energetic cosmic ray particles can have energies billions of times greater than those produced by the most powerful particle accelerators on Earth. This is why they are so fascinating to scientists. When these particles interact with the Earth's atmosphere, they create showers of secondary particles, which can be detected by special observatories. By studying these particles, scientists can learn more about the high-energy processes taking place in distant parts of the universe. Cosmic rays don't just travel across space, they also interact with matter in interesting ways. As they move through intergalactic space, cosmic rays can collide with gas and dust, causing a variety of reactions. These interactions can result in the creation of new particles, or cause changes in the material they encounter. For instance, cosmic rays can ionize atoms in the gas between galaxies, altering the properties of the intergalactic medium. These interactions can affect the chemical composition of the gas and influence the way matter behaves across vast distances. The journey of cosmic rays through space is also affected by magnetic fields. The universe is filled with magnetic fields, and they play a crucial role in guiding the paths of cosmic rays. These magnetic fields are present not only within galaxies but also in the vast regions between them. In intergalactic space, as cosmic rays travel, the magnetic fields can bend their paths, causing them to spiral and changing their direction. This is why, although we can detect cosmic rays here on Earth, it is often difficult to pinpoint their exact source in space. The bending of their paths by magnetic fields makes it hard to trace the particles back to their origin, which is why scientists have to use indirect methods to study them. As cosmic rays travel through intergalactic space, they can also encounter other high-energy phenomena, such as shock waves from supernovae or the intense radiation near active galactic nuclei. These interactions can alter the properties of the cosmic rays, sometimes even changing their energy levels. For example, cosmic rays can be energized even further as they pass through regions of space where matter is being compressed or heated. These additional energy boosts can lead to the creation of more powerful cosmic rays, which can then travel even farther. The energy from cosmic rays has an effect on the space they travel through as well. When cosmic rays hit the Earth's atmosphere, they can trigger a cascade of particles, creating what is known as a cosmic ray shower. This shower of secondary particles can be detected using special instruments, such as ground-based telescopes or balloons equipped with particle detectors. These cosmic ray showers help scientists study the properties of cosmic rays and the high-energy environments from which they originate. The study of cosmic rays is important not only because it reveals the behavior of particles, but also because it provides a window into the extreme processes occurring in distant parts of the universe. While cosmic rays have been studied for decades, they still present many mysteries. One of the biggest questions is the origin of the highest energy cosmic rays. While we know that supernovae and black holes are important sources, we don't yet fully understand how the most energetic cosmic rays are produced. Some of the highest energy particles seem to come from galaxies that are millions or even billions of light years away, far beyond the reach of any known source of energy. This has led scientists to consider the possibility of even more extreme events or objects that could be accelerating these particles to such high energies. One of the main challenges in studying cosmic rays is their rarity. The most energetic cosmic rays are extremely rare, and they don't interact with Earth's atmosphere very often. In fact, a single cosmic ray may pass through the Earth's atmosphere without triggering any noticeable effects. To detect these high-energy particles, scientists rely on large-scale observatories, often located in remote areas or even in space, to increase their chances of capturing the rare events when cosmic rays interact with matter. In the end, cosmic rays are more than just a curiosity. They provide important clues about the universe. By studying them, scientists can learn more about the extreme processes that occur in distant galaxies, around black holes and in the aftermath of supernovae. Cosmic rays offer a glimpse into the high-energy universe, showing us how the most energetic particles in space behave and interact. They travel across vast distances, carrying information about the farthest reaches of space. And in doing so, they help us understand the universe on a deeper level. At the boundaries of intergalactic space, there is more happening than might meet the eye. The vast, seemingly empty stretches between galaxies are not as quiet as they appear. These regions are filled with streams of high-energy particles and radiation that flow between galaxies and across the immense voids of space. While it might seem that the space between galaxies is empty, these invisible flows of energy carry with them critical information about the universe's structure and how galaxies interact with each other. One way to imagine these energy flows is by thinking of rivers. Rivers carry water from one place to another, moving energy through their flow. Similarly, streams of high-energy particles move through the gaps between galaxies, connecting them in ways we can't see directly, but can detect through their effects. These particles are often created in the extreme environments near black holes, supernovae, and other energetic phenomena. As they travel through the universe, they carry vast amounts of energy and can influence the surrounding space, even across enormous distances. The particles that make up these energy streams include protons, electrons, and atomic nuclei. They are often moving at near the speed of light, traveling through intergalactic space with energies far higher than those we experience here on Earth. The origins of these particles are many. Some of the highest energy particles come from the centers of galaxies, particularly from the supermassive black holes that sit at the heart of many of them. These black holes generate powerful jets of particles and radiation, sending them out into the surrounding space. Some of these jets can reach out into the vastness of intergalactic space, connecting galaxies across large distances. In addition to the particles generated near black holes, the process of supernovae, massive star explosions, also contributes to these streams. When a star explodes, it releases vast amounts of energy and sends shockwaves through space. These shockwaves can accelerate particles to extremely high speeds, creating cosmic rays that travel through space. The radiation from these explosions spreads across intergalactic space, affecting the gas between galaxies and carrying energy far beyond the galaxy of origin. These energetic flows are part of a much larger, dynamic system, influencing everything from the motion of galaxies to the behavior of the gas in the cosmic web. These high-energy particles and radiation can interact with the intergalactic medium, the thin gas that fills the space between galaxies. As these particles move through this gas, they can collide with the atoms and ions present, transferring energy to them. This process can heat up the gas, causing it to glow faintly in certain wavelengths of light. This is why, although intergalactic space seems empty, it still plays a vital role in the broader structure of the universe. The movement of high-energy particles and radiation helps to maintain the cosmic balance, transferring energy across vast distances and connecting distant parts of the universe. One of the most striking features of these energy flows is their ability to travel across voids. Voids are large regions of space where very few galaxies or stars are present. These areas can be hundreds of millions of light-years across and are thought to be the result of the gravitational pull of galaxies and clusters of galaxies. Despite being devoid of visible matter, these voids are not empty in the true sense of the word. Streams of high-energy particles travel across these vast gaps, carrying energy through regions of space that seem lifeless. These particles can pass through the voids without being absorbed or scattered, thanks to the low density of matter in these areas. Their journey across the voids is a testament to the power of energy flows in the universe, moving through space without much interference. These high-energy flows also have a significant impact on the structure of galaxies and galaxy clusters. When particles from distant galaxies or active regions interact with the gas in a galaxy, they can heat up the gas, trigger star formation, or even slow down the growth of new stars. The energy transferred from the radiation or high-energy particles can prevent gas from cooling and collapsing into stars, which is one of the ways supermassive black holes can influence their host galaxies. The radiation they emit, combined with the particles in the jets they produce, can impact the surrounding space in ways that scientists are still trying to fully understand. Even when cosmic rays and radiation travel between galaxies, they can leave their mark on the gas in between. These particles can ionize atoms in the intergalactic medium, meaning they can strip electrons from atoms, creating ions. This process affects the overall behavior of the gas in these regions. The ionized gas can absorb and emit light in different ways than neutral gas, which in turn can alter the way we observe the universe. By studying the effects of these particles on the gas in intergalactic space, scientists can learn more about the flow of energy across the cosmos and the forces at play in the largest scale structures of the universe. In some cases, these energy flows can even influence the motion of galaxies themselves. The radiation from supermassive black holes or the shock waves from supernovae can push against the gas in galaxies or galaxy clusters, affecting their movement. For example, In galaxy clusters, the radiation pressure from active galactic nuclei, the centers of galaxies with active black holes, can push gas out of galaxies, affecting how the galaxies evolve and how new stars form. The energy from these cosmic flows creates an environment where galaxies and clusters of galaxies interact with each other in subtle ways, shaping their future development. The energy that flows between galaxies also plays a role in what is known as the cosmic web, the vast structure that holds the universe together. This web is made up of filaments of galaxies and dark matter, connected by stretches of gas. The streams of high-energy particles that move through intergalactic space help to fuel this web, transferring energy and matter across the vast distances between galaxies. These filaments, and the energy within them, form the backbone of the universe's large-scale structure, influencing the formation of new galaxies and the behavior of matter across great distances. Despite the fact that we cannot see these high-energy particles with the naked eye, their presence is critical to understanding how the universe functions. The way that particles move across intergalactic space and interact with the gas between galaxies is a key piece of the puzzle when it comes to studying the large-scale behavior of the universe. These energy flows help maintain the structure of the universe and influence the interactions between galaxies, clusters, and even the empty spaces between them. In summary, the boundaries of intergalactic space are not as empty as they seem. Streams of high-energy particles and radiation move through the vast voids of space, connecting galaxies and influencing the gas between them. These flows carry energy across enormous distances, shaping the structure of the universe, from the way galaxies interact to how the intergalactic medium behaves. Understanding these energy flows helps us understand the universe on a larger scale, giving us insight into the forces that connect everything, even in the empty spaces between galaxies. Dark energy is a mysterious force that is playing a crucial role in the way the universe behaves. It is responsible for the accelerated expansion of the universe, a phenomenon that has puzzled scientists since its discovery. While dark energy has a significant impact on the universe as a whole, its effects might become even more noticeable at the edges of intergalactic space, where galaxies are spread apart and the influence of gravity weakens. To understand how dark energy might behave differently at the edges of intergalactic space, imagine a balloon being blown up. As the balloon expands, the space between the dots on the balloon's surface grows larger. Similarly, as the universe expands, the distance between galaxies increases. This expansion is driven by dark energy, and it is happening more rapidly than ever before. Unlike gravity, which pulls matter together, dark energy pushes things apart. This force is so powerful that it is overcoming the gravitational pull of galaxies, clusters, and even large groups of galaxies, causing the universe to expand faster as time goes on. Dark energy was first discovered when scientists noticed that the expansion of the universe was speeding up rather than slowing down, as they had once expected. They observed distant galaxies moving away from us faster than anticipated, which led to the conclusion that something was driving the expansion. This something was named dark energy, though its exact nature remains unknown. What we do know is that it makes up about 70% of the total energy content of the universe, and its effects are felt across the entire cosmos. Now, when we look at the edges of intergalactic space, the influence of dark energy might be more pronounced. At these outer regions, galaxies are farther apart, and the gravitational forces that would normally hold them together weaken. As a result, the expansion of the universe driven by dark energy becomes more noticeable. While gravity pulls matter together at smaller scales, the sheer scale of the universe means that dark energy becomes dominant over very large distances, especially in the regions between galaxies where gravitational forces are weaker. In the dense centers of galaxies and clusters, gravity is strong enough to counteract the effects of dark energy. Galaxies are held together by the gravitational pull of stars, gas, and dark matter and even the accelerating expansion of the universe can't break them apart. But at the edges of these galaxies, where the pull of gravity is weaker, dark energy can stretch the space between them. This causes galaxies to move away from each other at an increasing rate. The farther we look into the universe, the more pronounced this effect becomes, with galaxies at the outer limits of intergalactic space receding from us faster than those closer by. One example of how dark energy affects the universe at these large scales is the measurement of the cosmic expansion rate. Scientists use something called the Hubble constant to measure how fast galaxies are moving away from us. This rate has been observed to increase over time, which suggests that dark energy is pushing galaxies apart at an accelerating pace. As we look further into space, we see galaxies that are receding from us at speeds much faster than we would expect if only gravity were at work. This observation is consistent with the presence of dark energy, which accelerates the expansion of space itself. At the edges of intergalactic space, the effects of dark energy are particularly important because these regions are so far removed from the gravitational influences of galaxies and clusters. The farther we get from a gravitational source, the less influence gravity has. In these empty, low-density regions, dark energy has the freedom to push the universe apart without interference. This is why the expansion of the universe is accelerating in the first place. The farther the galaxies are, the more dark energy dominates the expansion process. This expansion is not just an abstract concept, it has real consequences for the universe. As galaxies move away from each other, the space between them grows larger. This means that, over time, distant galaxies will become increasingly unreachable. Eventually, some galaxies may be so far away that their light will never be able to reach us, as the space between us and them will be expanding too quickly. This is one of the reasons why looking at the edges of intergalactic space is so important. It gives us a glimpse into the future of the universe, where the vast distances between galaxies continue to grow, driven by dark energy. Dark energy's effects can also be seen in the large-scale structure of the universe. The cosmic web, which is made up of galaxies and dark matter connected by vast filaments, is influenced by both gravity and dark energy. Gravity draws galaxies together, forming clusters and superclusters, while dark energy pushes them apart, driving the accelerated expansion of the universe. The balance between these two forces shapes the overall layout of the universe, creating a structure that resembles a giant web with filaments of galaxies and voids in between. The edges of intergalactic space, where galaxies become more spread out, are where the forces of dark energy become most noticeable, pushing galaxies further apart and increasing the size of the voids. Despite our growing understanding of dark energy, it remains one of the greatest mysteries in modern science. We know it is responsible for the accelerated expansion of the universe, but we don't know exactly what it is. Some theories suggest that it could be a property of space itself, a kind of energy inherent in the fabric of the universe. Others propose that dark energy might be tied to quantum fields, or even some unknown fundamental force. Regardless of its true nature, its effects are undeniable. As we look toward the edges of intergalactic space, we see dark energy's influence growing stronger, pushing galaxies apart and shaping the future of the cosmos. The presence of dark energy at the edges of intergalactic space also has implications for our understanding of the universe's fate. If dark energy continues to drive the accelerated expansion, the universe may eventually reach a point where galaxies are so far apart that they can no longer interact with one another. The stars within those galaxies will burn out, and galaxies will drift through space, isolated in the vast emptiness. While this scenario is billions of years away, it offers a glimpse into the long-term future of the universe and underscores the importance of dark energy in shaping cosmic evolution. In the end, the effect of dark energy is felt most acutely at the edges of intergalactic space, where the expansion of the universe is driven by this mysterious force. In regions far from the gravitational influence of galaxies, dark energy dominates, causing galaxies to move apart at an accelerating rate. As we look further into the universe, we see the far-reaching consequences of dark energy, not only for the structure of the universe but also for its ultimate fate. Dark energy is a mysterious force believed to be causing the universe to expand at an accelerating rate. It makes up about 68% of the universe, yet we know very little about it. Scientists have come to this conclusion because of the way galaxies are moving apart. In the early 1990s, astronomers observed that distant galaxies were receding from us faster than expected, and it seemed that this speed was increasing. This led to the discovery of dark energy, a force pushing galaxies apart, counteracting the pull of gravity. But the effect of dark energy is not uniform. Some theories suggest that its influence could become more noticeable in regions far from the dense clusters of galaxies, such as the edges of intergalactic space. Intergalactic space is the vast emptiness between galaxy clusters. It is almost completely devoid of matter. In such regions, gravity from nearby galaxies and stars has little effect. This is where dark energy could have a stronger presence. Without the gravitational pull from stars or galaxies, dark energy might act more freely, pushing matter apart more effectively. Imagine a region where galaxies are scattered thinly across the sky, each moving away from one another. The force driving this movement could be more evident here, as there is less other matter to counteract it. To understand this, it helps to think of how forces act on objects. In a crowded room, if you push a ball, it will hit other objects and slow down. But in a large, empty room, that ball will keep rolling without any obstacles to slow it down. In space, the empty regions between galaxies act like that large, empty room. With less matter to interfere, dark energy has more freedom to stretch out the fabric of space, speeding up the expansion of the universe. One possible scenario to illustrate this could be how galaxies behave when they are far apart. In the middle of a galaxy cluster, gravity from nearby galaxies holds everything in place. These galaxies may move toward each other, or at least remain in a stable orbit around a common center. But as you move away from these clusters, the effect of gravity weakens. In these distant regions, dark energy could play a larger role. It could become the dominant force, accelerating the expansion of space and pushing galaxies farther apart. This difference in force is not just a theoretical idea. Observations of distant supernovae and the cosmic microwave background radiation support the idea that dark energy is more noticeable in regions far from galactic clusters. Supernovae, which are explosions of stars, serve as standard candles for measuring distances in space. When scientists observe how the brightness of these explosions changes with distance, they find that the universe is expanding faster than expected. This could be a direct result of dark energy's effect becoming stronger in the voids of space. In the early universe, matter and energy were more evenly distributed. As the universe expanded, gravity caused matter to clump together, forming galaxies and stars. During this process, the expansion slowed down. However, as galaxies and matter became more spread out, dark energy began to dominate. It counteracted the effects of gravity, causing the acceleration we see today. This means that at the edges of intergalactic space, where matter is sparse, dark energy's influence is much more pronounced. This is a key reason why scientists are so focused on studying the outskirts of galaxy clusters and the empty spaces between them. Understanding how dark energy behaves in these regions could provide clues about its true nature. For instance, if dark energy behaves differently in the vast emptiness between galaxies, it could suggest that it is not a constant force. It might change depending on the environment, becoming stronger or weaker depending on the amount of matter around it. To further explore this idea, scientists use sophisticated instruments like the Hubble Space Telescope to study the light from distant galaxies. Light travels through space at a constant speed, but it can be stretched as it travels across the expanding universe. This stretching causes the light to shift toward the red end of the spectrum, a phenomenon known as redshift. By measuring redshift, astronomers can determine how fast galaxies are moving away from us. This data shows that galaxies are not just moving away from each other, but that the rate at which they are receding is increasing. This acceleration supports the idea that dark energy is driving this process. The effects of dark energy could also be tied to the geometry of space itself. General relativity, Einstein's theory of gravity, tells us that mass and energy can curve space-time. When there is more matter, space-time bends more and gravity becomes stronger. But dark energy seems to have the opposite. Instead of pulling matter together, it pushes space apart, causing space-time to stretch. This stretching happens more significantly in regions of low matter density, such as the edges of galaxy clusters. The more we learn about how space-time behaves in these distant regions, the better we can understand dark energy's role in the expansion of the universe. In regions of intergalactic space, where galaxies are isolated, dark energy could even cause objects that are already moving away from us to speed up further. This could make the universe's expansion rate increase over time. The implications of this are profound. If dark energy continues to push galaxies apart at an ever-increasing rate, the distant future of the universe could look very different from today. Over billions of years, the galaxies could become so distant from each other that they will no longer be visible from Earth, as their light will be stretched beyond the visible spectrum. One interesting aspect of this scenario is that the accelerated expansion of the universe might not have always been so noticeable. Early in the universe's history, gravity was the dominant force, and it was only as the universe grew older that dark energy began to assert itself. In regions where matter was sparse, dark energy could have had a more significant role earlier on, while in areas dense with galaxies, it may have taken longer for dark energy to become dominant. The interplay between dark energy and the distribution of matter across the universe is still a topic of intense study. While we cannot directly observe dark energy, we can infer its presence and influence by looking at how galaxies and other cosmic objects behave. Understanding its effects, especially at the edges of intergalactic space, will be crucial for shaping our knowledge of the universe's future. Intergalactic space, despite its appearance of emptiness, is not completely devoid of matter. Even though the vast stretches between galaxies are mostly empty, they contain tiny particles of dust. These particles, while sparse, come from a variety of sources including stars, supernovae, and other cosmic events. The density of this intergalactic dust is incredibly low compared to the dust found within galaxies, but it still plays a role in the overall makeup of the universe and can have subtle effects on the light and energy traveling through space. Imagine standing in a dark room. Although the room may appear empty, if you shine a bright light, you might notice small particles floating in the air, catching the light and scattering it. This is a bit like what happens in intergalactic space. While the space between galaxies might seem empty, light traveling through it can interact with the tiny particles of dust scattered throughout. These particles are incredibly small, often just a few microns in size, but they can still affect the way light behaves as it moves across the cosmos. The dust in intergalactic space comes from several sources. Stars, particularly those that are massive, often release dust particles as part of their life cycle. When a star reaches the end of its life and undergoes a supernova explosion, it blasts huge amounts of gas and dust into space. This dust, made of heavier elements such as carbon, oxygen, and silicon, can then travel across vast distances, carried by the winds of space. This material can eventually find its way into the vast emptiness between galaxies, contributing to the small but steady presence of dust in intergalactic space. Another source of intergalactic dust is the gas clouds that exist in and around galaxies. These clouds, made of ionized hydrogen and other elements, can also contain small amounts of dust. As gas and dust are ejected from galaxies or collide with other cosmic structures, some of the particles can be scattered into intergalactic space. Over time, this process contributes to the spread of dust throughout the vast expanses between galaxies. Despite the fact that intergalactic dust is sparse, it still plays an important role in the behavior of light and radiation across the universe. When light from distant galaxies or stars travels through intergalactic space, it can encounter these tiny dust particles. As the light interacts with the dust, some of it is absorbed or scattered, causing subtle changes in the light's path. These interactions can affect the way we observe distant objects. For example, light from distant galaxies may appear slightly dimmer or have a change in color because of the scattering or absorption caused by the dust. This phenomenon is known as intergalactic dust extinction. The impact of this dust on the light we observe is a crucial tool for astronomers. By studying how light from distant galaxies is affected by dust, scientists can learn more about the properties of the dust itself. For instance, they can determine how much dust is present in different regions of space and understand the composition of the dust particles. This information can help scientists create better models of the intergalactic medium, the sparse gas and dust that fills the space between galaxies, and understand how it interacts with other elements of the universe. While the amount of dust in intergalactic space is small, compared to what we find inside galaxies, it is still enough to influence the way we study the universe. One of the most significant effects of intergalactic dust is its role in the cosmic microwave background (CMB). The CMB is the faint radiation left over from the Big Bang, and it fills the universe. As light from the CMB travels through space, it can pass through regions with varying amounts of dust. The dust in intergalactic space can affect the way we observe this radiation, altering the CMB's intensity and frequency. Studying these effects helps scientists learn more about the history of the universe and how it has evolved over time. Dust in intergalactic space also contributes to the process of star formation. While the concentration of dust is much lower outside of galaxies, small amounts of it can still have an impact. Dust plays a role in cooling gas clouds, helping them to condense and form new stars. When these clouds of gas and dust contract under gravity, they can form new stars and planetary systems. Although most star formation takes place inside galaxies, the presence of dust in intergalactic space may play a subtle role in the larger scale process of galaxy formation and evolution. The dust in intergalactic space is also affected by the forces that shape the universe. As galaxies move through intergalactic space, they can interact with the dust around them. For example, as a galaxy moves through the cosmic web of gas and dark matter, it can drag dust along with it, affecting the distribution of matter across the universe. These interactions can contribute to the growth of galaxies, as the dust and gas in the space between galaxies may be drawn into a galaxy's gravitational pull, helping to fuel star formation or create new structures. Despite being spread thinly across the vastness of intergalactic space, the dust still has a noticeable impact on the behavior of light and the distribution of matter. It is a key component of the intergalactic medium and plays a role in shaping the way galaxies, stars, and other cosmic structures evolve over time. Even in the emptiness between galaxies, where matter is sparsely distributed, these tiny particles of dust contribute to the larger cosmic processes that shape the universe. In terms of its composition, the dust in intergalactic space is similar to the dust found inside galaxies, though it is much less dense. The dust consists mainly of small grains of material that are formed from the remnants of stars and supernovae. These grains are made up of elements like carbon, silicon, and iron. which are created in the cores of stars and spread throughout space when those stars die. The dust particles in intergalactic space are often very small, sometimes only a fraction of a micron in size, but their presence can still influence the way light travels across vast distances. In conclusion, while intergalactic space may seem empty, it contains small particles of dust that come from stars, supernovae, and other cosmic events. These particles, though sparse, play an important role in the behavior of light, radiation, and the formation of galaxies and stars. By studying intergalactic dust, scientists can learn more about the composition of the universe, how galaxies interact, and how the universe has evolved since the Big Bang. Despite its small presence in the vast stretches of space, intergalactic dust contributes to the ongoing processes that shape the cosmos.